And so what I would like to present to you is a work where on elastocapillarity, and what we mean by elastocapillarity is when surface tension can deform elastic objects. And this is, so I will try to make a more like a review, which is based on a review paper that we wrote with my colleagues Benoît Roman and Etienne Ressa, and more generally with a MechaWeight group we have in Paris at the PMH laboratory. So the outlines are, well, this one. So I will first start with 3D and how a droplet, or more generally surface tension, can deform an object in the 3D. Then I will move to 1D. How that will be the problem of wet hair, like when you have a rod, how can a droplet deform a rod, if you like, surface tension deform a rod. And then I will move to 2D, how a droplet can deform a sheet. And in these 3 cases, so I will go quickly, and basically the point will be to define length scales, in which length scales surface tension is able to deform a solid body, depending on these 3 dimensions. So I would like first to start with a 3D case. So you know that when you take a chunk of a piece of liquid out of a liquid bath, for instance, if you take a cube or whatever, you need to create some interface that costs you a certain energy. This energy will be proportional to the area that you're creating. And if you have a liquid, you can deform this liquid, and usually this liquid will get deformed in order to minimize this energy. And well, this is something very well known. If you have a small amount of liquid that you isolate from a bath, you will end up with a liquid droplet which is spherical, which minimizes the surface energy. And the pressure inside the liquid will be given by the ratio of the surface tension of the liquid divided by the radius of the sphere you're doing. Now, if you do the same with the solid, in principle, you should also pay some surface energy as you remove a cube of solid out of a solid bulk. And you may wonder why could you deform this solid, or could you minimize the surface by making like a spherical shape? Well, of course, a solid is not as deformable as a liquid, and you have a Young modulus. So maybe you have something that the 2 ingredients can play together. And what people have been thinking for a long time, actually, is that actually if you take a cube of solid, remove it from a bath of solid, if I could say, what will happen is that the corners of this cube would be round up with a certain typical radius of curvature. And how do you find this radius of curvature? Well, basically you balance the surface tension, the Laplace pressure that I defined before, with this Young modulus, which is also a kind of a pressure, and you will end up with a length scale, which I will call it, I don't know, the stretching length scale maybe, which is the ratio of the surface tension of the involved, so in that case of the solid versus air, divided by the Young modulus of the solid. And for a long time it was just more like I would say like a curiosity, because if you put numbers for like a standard solid about Young modulus of gigapascal, on the order of gigapascals, the surface tension is about newtons per meter. You end up with a length scale which is about nanometers, so it's very, very small. But if you move to small soft gels, so very soft objects, for instance, Serge Morin in Montpellier has developed a lot of very, very soft gels. You end up with length scales which are on the order of 100 microns or even millimeters for very, very soft gels. And as you can see, these were cubes of gels which are removed from a cast. And as you can see, the corners are indeed round up with this typical radius of curvature. And you can also find it, for instance, in this granulated, this is a granulated gel, which was removed from a template of more rigid PDMS. And as you can see, the PDMS is very well granulated. That's the soft gel that you removed from this cast, rounded up, also with a typical curvature, which is this ratio of the surface tension by the Young modulus. So this was a pure solid. What could be interesting also is to see the effect of putting a droplet on the surface of a solid. Usually, when you look to class books, what you find is the Young relation, And this long relation says, okay, if you put a droplet on a solid, around the contact line of the droplet, you have 3 surface tensions which are pulling in the direction. So you have the solid vapor.
Excuse me, that's a liquid droplet?
This is a liquid droplet, yeah. Yes. Yeah, on the solid. So blue. Yeah, exactly. So blue. Well, in all the sketches, the blue will be the liquid droplet, and the reddish, like the elastic. Yeah. So what is presented in class books is, well, you have this drawing with a liquid droplet sitting on a solid, and you have the surface tensions pulling in the side. So you have the solid vapor, solid liquid, and liquid vapor pulling a bit up. And if you do the horizontal balance, you end up with a very classical Young relation, which tells you which is the contact angle of the liquid on the solid. But actually, you may wonder, okay, I've got this horizontal balance, but what about the vertical balance? It seems that it's unbalanced. And if you look in more details, actually, you will find out that, well, there is a vertical balance. You have a restoring force from the solid. And if you have a restoring force, that means that the solid is slightly pinched at the vicinity of the contact line. How do you find the order of magnitude of this pinching, if I can say? Well, basically, you balance the surface tension by the Young modulus times the deflection of the solid, and you end up with the same length scale, which is the surface tension divided by the Young modulus. So again, if you have like water on a glass, you end up with very small scales. But if you have again water, but on the very soft gel, that will be the next slide, then you can find this little pinching at a micrometer scale. So here, for instance, this is an experiment. You have it's maybe a bit difficult to see. You have water. The droplet is like that. The gel is a very soft gel of 3 kilopascals, so very soft. Here on this side, and you see that you have a little pinching. There are a lot of work from Eric Dufresne's group on this field, and so they were able to measure very carefully this region. And they also saw deformation on the micrometer scale, and the scale again is the surface tension divided by the Young modulus. And more recently, there is a nice work from Repstyle, was working with Eric Dufresne actually now on what they call durotaxis. So what basically they have a rather thin layer of very soft gel on a plate, but there is a gradient of thickness of this layer. And what they observe that if they put a droplet on this gradient of thickness, the droplet will move towards the thicker side of the gel. And so if you have like, if you can imagine having a gradient of thicknesses, well, patterns of thicknesses, and you can make, for instance, here lines where the droplet will move towards these kind of lines, or Y shape, or like funny shapes if you like. Okay, so that was for the first case, so the 3D. Now I will move to the 1D case, so we'll call it wet hair. And the experiment I would like to, well, the configuration I would like to discuss first is this following. So imagine you have a rod inside a droplet. The droplet is very small, floating on the air, if you like, so there is no gravity. And you have a little rod inside. And imagine that the water evaporates. So, if you could also imagine that the rod grows. That can happen for living objects. But imagine the water evaporates, so the volume decreases, and eventually the rod will touch the interface of the water interface. And the question is if the droplet keeps reducing its size, will the rod pierce the interface, or will the rod buckle and in order to remain inside the droplet? And well, you can compute what would be the capillary force if the rod was piercing the droplet. So you have a capillary force which is simply the surface tension of the liquid times the perimeter of the rod. And you know that if you have a compressive force, if I have a rod like that and if I compress it, it will buckle. This is Euler's buckling, very classical. And you know that you have a critical force derived by Euler, which is given by the bending stiffness of the rod. So I is the second moment of inertia, E is the Young modulus, divided by the square of the length. And basically, you expect the rod which is inside the droplet to buckle and to remain inside the droplet if this capillary force is bigger than this buckling force. Very, very easy. And you end up with a buckling length, if I can say, which is given by the square root, because you have L square here. So that will be the square root of the Young modulus times the second moment of inertia, divided the perimeter and the surface tension. So maybe I can give you like a couple of examples for the geometry of this rod. So if, for instance, if you have a rod like of a certain radius, little r, well, this bending length will be the square root of E r cubed over gamma, the surface tension. And if you another geometry which is useful would be like a lamellar geometry where we have let's say a lamella of thickness T, and in that case you get exactly the same kind of formula but with a T instead of R, and the prefactor will be slightly different, but basically you get the same thing. Okay, so okay, what can you do with this force? So I would like to present you an example, a very nice experiment done by Hervé Lettrou and Arnaud Ankoviak in Paris. So basically, the experiment they're doing is the following. So they have a very thin thread that they maintain between which is all in the two sides, and they put a tiny droplet in the middle of this thread, and the configuration is such that the size of the droplet is much larger than this bending length. So you will expect the thread to buckle, but since you maintain it, it does not buckle because it's maintained in both extremities. But then what they're going to do is to approach the two holding points of the thread. So you move the thread like that, and let's see what happens. So I move up. No, it's not moving. Okay, here it is. So as you see, as you compress the rod, all the fiber coils inside the droplet. So you can compress the rod like that. You can stretch it again, and well, you can do it. It's very, very robust. So maybe I will move up because the movie lasts like a couple of minutes, I think. But you see, it's super robust. And well, I find this experiment very interesting because it goes back to another program which I knew from this beautiful. I don't know if you probably in England this guy is very, very famous. I really love all these programs. Do you know David Attenborough? So he has one of the programs he has is Life in the Gross on the BBC, and it tells about insects basically, and he has a very nice little program on how spiders spiders make their webs in order to capture flies or insects. And basically the problem with the spiders is that when you have a fly impacting the web, well, you don't want the fly impact the web. The web is an elastic thing, so it responds elastically. But then you don't want the fly to bounce back as if it was jumping on a trampoline. And actually, what they say in this program, and it was well, it was based on some scientific results from Volra, is that if you look carefully to the radial threads on the webs, on spider webs, what you find is tiny little droplets, which are not droplets of dew. They are like a very gluey, very viscous liquid. But you have these very tiny droplets, and inside these droplets, actually, you have an excess of length of the thread. And basically, what happens is that when the fly deforms the web, these little droplets get, or the thread inside the droplet gets uncoiled. You deform a lot the droplet, and since it's a viscous liquid, you have viscous dissipation, and in the coiling back, you have since you have a viscous liquid, it takes some time to coil back, and you have a damping effect, which allows which prevents the fly to bounce back. Very, very smart system, I think. And okay. So you can over there. Okay, that's nice. You have this bending length. How can we measure it? So a very simple experiment you can do is the following: you take a lamella or like a rod. You put some water in both extremities. So yeah, I've got water here and here, and I fold it in order to make like a loop, to make like a racket, if you like. And you end up with such a racket. So, so maybe it's not obvious, but here you have some liquid meniscus. This is blue liquid, and the red racket will be like that. And what you can show easily is that, well, what sets the shape of this racket will be a balance again between surface tension and the bending stiffness of the racket. So you expect the width of the racket, for instance, to be proportional to this bending length. So that's a way to measure this length. You can do it also at a very large scale. So here I don't have capillarity, but I've got an elastic rod. I put some Velcro, so it's not a liquid, but it's also kind of adhesive on both sides, and I can stitch it like that. And you end up also with this. Okay, trust me, it's exactly the same shape of the racket, and so the shape itself is independent of on the scale. So you get this shape is universal, but the width, or if you prefer the length of this racket, will be proportional to this elasto bending length. So a very convenient way to measure this length scale. And one thing also which I find interesting is that if you look at the curvature close to the meniscus region, so you see that the shape starts with a certain curvature. You can easily compute this curvature by saying, okay, how do I find the curvature? I've got a liquid here, a meniscus. Since I've got a curved interface, the liquid inside the meniscus has a pressure lower than the atmospheric pressure. This is a Laplace pressure jump. So, and from this pressure, I can compute a force, and I can compute a torque. And then what is funny is that the torque is independent on the volume of the meniscus. And you balance this torque with the bending moment of the rod. And so basically what you find out is that the curvature, the initial curvature you have in this bracket, in this object, you have a curvature jump, and this curvature is this bending length, and this is totally independent from the boundary condition. So in whatever problem, when you have something sticking, a rod sticking on a solid, it starts with a curvature which is given by this bending length. And one of the consequences, so once you have this ingredient, you can solve a lot of problems. For instance, you can, well, this was for one hair. You can also wonder what happens if I have got many hairs. So in my case, I cannot do this experiment, but this guy has a hair long enough to do this experiment. So, well, you know that it makes bundles. Well, it can be for fun, but it can be also a big issue in microfabrication, because when you go down to small scales, capillary forces become very important. And there are a lot of issues of objects getting destroyed, microstructure getting destroyed when you remove them from a solvent. And this is a big issue in microfabrication. Here is photoresist, which structures that collapse. Here, this is a caplet of carbon nanotubes that kind of collapse into this cellular structure as you put a liquid on it and let the liquid evaporate. So it's a big issue. And if you want to understand this, but you can also use this elastocapillary, I can say clumping, as a way to make structures. So here, for example, I've got an example where in this group they have made like arrays of regular pillars. Since the array is regular, they can diffract light, and so they have a certain color, or red and blue, depending on the angle you look at it. When you put this array in water and remove it from the water, these arrays may be these little clumps. They don't have all the same size, and then instead of having like a nice diffraction pattern, you find like a whitish surface. But one of the biggest specialists in making very nice structures with this elastocapillary assembling is not so far from here. Michael de Volder, with I guess he has been in Cambridge for a couple of years, and he's able to make like very beautiful structures with carbon nanotubes, so at very small scale, and basically they are assembled by this elastocapillary adhesion. So, back in Paris, we looked at this elastocapillary adhesion process. So basically, it's a kind of, so we did experiments with artificial brushes, model brushes that you remove from a bath of liquid. And what you see is that basically the clumping mechanism is done by relies on the association of two small objects that later on, two small lamellas that later on associate with another object, which later on associate with another object, and so on. So you have a kind of cascade of coalescence, if you like, where you have pairs of lamellas that connect with bundles, which connect with bigger bundles, and so on. But the main ingredient is to stick together two flexible objects. And how do you find the sticking length at which these two objects connect? Well, you use a little trick that I taught you before about the curvature. So here, for instance, you have a meniscus. So what we said before is that the curvature here should be given by the inverse of the bending length. How do you find in a scaling law this curvature? Well, basically, this is the distance separating the two flexible objects by the square of the sticking length. That gives you an order of magnitude of the curvature. And when you balance these two quantities, you end up with a very simple relation that tells you that the length at which two flexible objects connect is set by the product of the square root of the distance separating the two flexible objects and the square root of this bending length. And then this is where we also Ariski was in the loop as well. So you can generalize so for multiple for bundles of more than two objects, and well, basically you get the same law. So L2 is for two elementary objects, and depending on the geometry, you can have the number of the final sticking length will be proportional to the number of the elements involved in the bundle to the power 3/4 if you have in a 1D array, or 3/8 if you have in 2D. Well, it's more a detail. Anyway, so just to show you that things are not always that simple. So there's a very nice experiment from Camille Duprat. Oops, okay. So basically, I will stop the experiment so that I will spoil the. I would prefer to explain you before. So basically, she has two little fibers sticking out this way. So they are clamped on the left. And she puts a droplet of water, or silicone oil in that case, I guess, in the middle of these two little fibers. So as you put the droplet, as you can see, the droplet moves towards the end because so that it bends the fibers. And if you add water, well, basically you end up with a meniscus which is about the same distance. But if you have too much water, you see you may expect. Oops, sorry. So if you put a little droplet, it stops. Oops. Oh yeah. Anyway. Okay. So if you put a single droplet, it will stop basically at the length we defined before. So it's okay. If you add a second one, it will move a bit closer to the clamping point. Okay, well, you say, okay, maybe this length was not so precise and so. But what is funny is that if you add even more water, instead of moving to the clamping base, it moves on the other direction, which basically tells you that well, you should be careful with what I told you before. It's maybe a very simplified view. When you deal with rods, you have another length scale, which is the curvature of the rods, and that may play some little tricks as we have in this case. Okay, that was the end for the wet hair problem. So now I would like to quickly move to drops and sheets. So what happens if you put a droplet on a sheet now? And basically, well, I will start with a very simple experiment. So imagine you have a flexible sheet whose length is larger than this bending length that I defined before, and I will put a droplet on it. So since this length is larger than this bending length, you expect probably the sheet to wrap around the droplet, because capillary forces should be able to bend this sheet. So is it going to work? Well, yes, it will. So here this is a triangle cut from a thin sheet of PDMS, silicon if you prefer. So the edges of this triangle is about a couple of millimeters. The thickness is about 50 microns, and this is silicon, so it's pretty soft. We're going to put a droplet on it. Okay, this is there is a blue dye in the droplet, so you can see it better. And as you put the droplet, on it, what you can see is that, well, okay, maybe I will explain you the experiment before. Okay, so basically we put the droplet and then we let it evaporate. And the idea is to look at the shape the object gets as the liquid evaporates. So first you make like you first make like well, the triangle tend to wrap around the droplet, and as the volume decreases, you end up with a pyramid shape. The pyramid is not perfect because you see you have some openings, so the water can still evaporate. So it evaporates. You almost close your pyramid, but then at the very end, since the water keeps on evaporating, the pyramid kind of implodes, and eventually it opens again. But actually, if you play some tricks, for instance, you can put some polymer inside the droplet, so that you can stick the edges of the pyramid, and you can maintain the 3D shape if you wish after the water has totally evaporated. So this kind of technique has been used at much smaller scales. So this is from a group in 20. So they make like a little cubes that closes when you put a droplet. Or very nice work also from David Gracia's group. So basically they do it at very small scale. The scale bar is like 200 nanometers, so it's very, very small scale. They have templates with hinges in that case, so they are easier to bend. They with vapor, they vaporize some solder on the surface of this little template. And as you heat up the surface, the solder droplets melt, so capillary forces can come into action and close the structure. And as you cool down the sample, the droplet or the solder solidifies again, and you end up with a static with a robust little cube. In that case, at a very small scale. There are also the recent work which I like very much from the group in there is a very nice group in Amherst with Menon and Benina Lidovich and so on, and this is from Paulsen. This experiment from Paulsen. So basically, he does the same kind of experiment with a very, very thin sheet. So in that case, the length of the sheet is much larger than the bending length. So basically, it doesn't cost anything to bend this sheet. It's so thin that it doesn't cost anything to compress as well. You can make wrinkles. That's a way to compress a sheet without. And so they have looked at the final shapes you get as the water evaporates. And in that case, you get like a samosa kind of shape. So it's very interesting shapes. And what I find interesting is that you have a very strong analogy with this problem between this problem and the here in Cambridge also, and the problem from J. Taylor's on the parachute. I don't know if you know this work. You can find it in the. It's not easy to find. You need to go to the whole 4 volumes book on J. Taylor's works. But very nice work on the shape of on the parachutes, and basically you get the same kind of description, and the mathematical problem that you encounter is to find an optimum volume, and the ingredients, what you have to impose, that you have, you have no stretch, and you are free to bend and compress your sheet. Very nice problem. So I would like to finish with some other cases which are a bit more tricky. So what happens if now I put my sheet on a solid droplet? So how can I do that? Basically, sorry, I am spoiling the. So you take an adhesive sheet, for instance, or if you prefer, you take a sphere, put some liquid on it, and put a non-adhesive sheet on it. But since you have some liquid on it, the capillary forces will provide some adhesion. And what do you observe? Well, actually, what you observe is a funny shape. If the sheet is soft enough, is thin enough, you get this kind of strange pattern. So Maybe it's not easy to understand. So everything is transparent. So the sphere is transparent. This is a Christmas ball, if you can see. You have a sheet on the top of it, and this wavy region is the contact between the sheet and the sphere. And we see it better because we put some blue dye, so it's a bit a mess, but there is some blue dye, so you can see the meniscus better. So all this region here is a contact region between the sphere and the sheet, and apart from this region, the sheet is not in contact with the sphere. And but it's kind of messy, but what you can define in any case is a typical width of this region. So you can try to find what is well, if you prefer, if I had a very small patch smaller than this region, I would be able to stick it on the sphere without making any wavy, any funny shape. But if I have something larger, I start making this wavy shape. And when you think about it, well, actually, you're trying to find well, wrapping a sphere with the sheet is a very old problem. Maybe the oldest problem is trying to map a sphere into a sheet. So people who are trying to, well, for a long time, have been trying to make maps of the Earth. And you know that whatever projection you choose, it's impossible to map a spherical shape into a flat shape without distorting distances. It was proved more mathematically by Gauss, but it was known for a long time that you could not make a map of the Earth without deforming the continents. So here it's a bit the same. If you want to force a flat sheet to adopt a spherical shape, you have to somehow to stretch it. So which means in the regions of contact, you have no way. You are obliged to stretch a bit the sheet. And so you can say, okay, I have to stretch it, so I will have to pay something to stretch it, but I have some addition, so I gain something. So can I compute? Can I compare the price of stretching with the price of addition? So it's not, in terms of orders of magnitude, it's not so difficult. You can, by pure geometry, you find out that the stretching strain, a typical stretching strain, is the square of the ratio of the size of your disk by the curvature of the sphere to the square, and you get a stretching energy which is proportional to this strain to the square. Okay, and you balance this. You can try to balance this stretching energy with addition energy, which is simply the surface tension of the addition energy of your adhesive times the area that of contact, and you end up with this typical area where you are able to, where the two things balance, which is proportional to the radius of curvature of the sphere, and to a non-dimensional number, which is a ratio of the surface tension of the liquid, or the addition energy of the adhesive, divided by the stretching modulus of the sheet. And the stretching modulus, you get it by multiplying the Young modulus by the thickness of the sheet. And you take this number to 1/4, and you get this typical contact region between the sheet and the sphere. And I would just like to finish with one experiment which is very nice, but it has been quite complicated to. A lot of things have been derived. It motivated a lot of studies. So it's the following. So it's an experiment from Menon's group. So basically, so what Menon do, he takes a very thin sheet of polymer. But when I say thin, it's about 100 nanometers. They cut a disc, put it on let it float on the surface of water. Okay, so far so good. And then it takes a very small droplet of water, put it in the middle of the sheet, and small enough, and the droplet is small enough so that gravity does not matter. And what he observes is very nice, this very nice pattern. So this is a view from above. So this is a droplet, and as you deposit the droplet on your sheet, you observe these little wrinkles, which are, well, first they are very nice, but you can learn a lot of things from these wrinkles. So basically, what do you get wrinkles? Well, as you push the droplet, you have two kind of surfaces or forces that enter into the game. So you have a curved interface. So you have a Laplace pressure that tends to push down the sheet under the droplet. You also have like contact lines that tends to pull up the sheet. And you also have surface tension along the periphery of the sheet, and tends to pull towards the sheet. So you have a kind of funny balance with this surface tension. And what they find out is that if you count the number of wrinkles around the droplet, this number is related to the bending length scale by this relation. So basically, by measuring the number of wrinkles, you can deduce the bending length scale. And one issue which was a bit more tricky to, and I'm not certain that maybe Dominique Vella can confirm what is the best relation. But if you measure the length, the typical length of these wrinkles, this length scale is defined by the balance between stretching and surface tension, and should be proportional to the radius of the sphere and times this non-dimensional numbers that we had before. Is it 1/2 or 1/3? There is still some little debate. I guess the last version is 1/3, but maybe Dominique, if he's around, can confirm. And okay, just to summarize, maybe I'm late, I guess. So we have three geometries. We have two length scale and one non-dimensional number. So for 3D, basically what you have to remember is that the length scale is gamma over E. Okay. Usually that's a small scale, but if you go to very soft solids, maybe you can see it. Maybe more for something which is more practical is a kind of 1D case where you have a bending length scale, which scale is the square root of the ratio of the bending stiffness by the surface tension. And when you deal with the sheets that you have to stretch, you have something which is not a length scale but a non-dimensional number, which compares the surface tension and the stretching stiffness of your sheet. There are some still open questions. Since I wanted to make a review, so I want to make an open question. So many of them are kind of open questions are connected to dynamics. So it's something which is still, I think, not so easy to define. So, for instance, what are the dynamics of these little ridges as a droplet? For instance, if you put it in an incline, the droplet will move. But what is the dissipation in these little ridges? A very non-trivial question. In the aggregation dynamics are also different models, and I'm not so sure that what I've presented you is a truth for like any. Well, it's a universal description. There can be other possible description, especially for shorter hairs. And in case of sheets, well, when you deal with sheets, it can be like you can end up with very complicated crumpling issues, and there are still open questions. And I just have the last slide. So other strategies to deform slender structure. So I guess Doc Holmes will tell us about swelling. So here is a mixing about capillary and swelling. Here in the lab, back in Paris, we have been playing with electroactive membranes. So there are also some analogies in some sense with surface tension. And maybe in connection with the talk with Amir Gat, which later in the week, we are also playing with pneumatic pads, and you can make a mask that out of 2D. Well, we are very interested in transforming 2D objects in 3D shapes, so we are making masks now. Okay, thank you very much.
Right, so we have time for maybe a couple of questions before I speak.
In the experiment you showed where you pull the thread and when you relax it, it goes into the drop. Is the tension in the thread constant, or is it expected to be a constant?
So no, that's a good point. So what they measure is that the force is constant actually. So if you measure the pulling force, I guess yes, they did it with a very precise load cell. So, well, if you take like an elastic rod, where you have an elastic response and the force increases as you stretch it. In that case, when you have the coil, you can uncoil the coil, if I can say, uncoil the thread with a constant force. So it's a very original mechanical behavior. Yeah, it's very nice.
Had a picture of the person with the big
yeah.
pointy tattoo. So when you use hair gel.
Exactly. So you if you like, I guess you increase adhesion if you like. So you increase surface tension. So you increase the gap interne, I would say.
So I was going to ask you, hair gel is a gel. It's not fluid. So what role is the actual material properties of the
well, I guess the point that with gel you have something more adhesive, more viscous, so which costs more energy to pull apart, I guess. And also you probably rigidify because as you could see, well, in that case I took like a very extreme, case, but the hairs do not fall in under their own weight, which is also due to the fact that the gel stiffens quite a lot the hairs.
Yeah, I've noticed the same thing with soap. So when you have a 4-year-old daughter, when you can make a really big spike with soapy.
Yeah. Yeah. But okay, maybe a more appropriate picture would be somebody like with military short hair. With when you wash the hair, it makes like little clumps. That would be more this kind of, or the more appropriate image would be more this one. Well, I chose this one because it's more spectacular, but maybe it's a bit slightly misleading. But in that case, there is indeed some gel, and first it rigidifies the structure, and it also makes the adhesion stiff, or the adhesion stronger.
Great. When you were showing this picture of a droplet with a small fiber and raised the question of whether it would buckle or poke through, it reminded me of an experiment that Deborah Feigenson did about 20 years ago on microtubules in vesicles.
Yeah, indeed, yeah.
So we could have the competition between an induced tension and the membrane.
Indeed, yeah. I think there are, well, it's reference. So there is a paper from Cohen and Madivan, and I think there are different examples in this paper, and they mention this case. So indeed, you can also consider like rigid structures in vesicles, or like indeed, very interesting. And basically you get somehow the same kind of idea. Well, you could also have some specific issues due to the fact that if you have like an envelope, it's not exactly like having like a surface tension. Well, it depends if you can shear or not the envelope. I mean, it's not.
Well, in this case, the membrane had its own elasticity.
Exactly. Yeah. But yeah,